Okay, here I wanted to talk through a couple examples using quadratics in order to solve application problems. Okay, so with these, the biggest thing that you have to remember is that one, you are probably going to be given the formula, and if not, then you have to look at the information provided in your problem in order to create the formula. So here we're going to start out with a physics idea, so a physics application, and the formula we need is this one right here. This is your projectiles formula, and this deals with velocity as well as initial height. So notice we have T here, stands for your time. V naught is your initial velocity that the projectile is traveling, and H naught is that initial height. In other words, it's the starting place before your object is set in motion. So here we have a problem that we have to try and solve, and notice nowhere in this problem are we actually given the formula. Well, that's because we have to create it. So we have that a projectile is fired vertically upwards from a height of 200 feet above the ground with an initial velocity of 1100 feet per second. So what does this actually tell us? Well, this tells us that our H naught, or initial height value, is 200 feet. The other thing it tells us is that V naught value, or that initial velocity, which is 1100 feet per second. So with that, we have everything we need in order to create our equation, which, if you notice, that's the first question, which says to write the quadratic equation to model the projectile's height in feet above the ground after t seconds. So here, what do we know? Well, we know h of t is going to be my height after t seconds, and then I have negative 16 t squared plus I have to add my initial velocity, which was 1100, and then t, plus my initial height, 200. And that is all you have to do right there. This is now our formula. You can see it's modeled in terms of h of t, and we're finding t as our variable. So everything else has been filled in with the exception of our time. The second piece wants to know the time interval that the projectile will end up being more than 8,000 feet above the ground. So if we're thinking about a graph, okay, in terms of this problem, if we're thinking about our graph, this would be t for time, and this would be your max height, or your height, okay? And here we're actually looking at, it's a big giant parabola, okay? Because what do we know about physics? Well, when you throw an object up in the air, it's going to travel up in the air for a certain period of time. It's going to reach a point where it cannot go any higher, and then it's going to start coming back down again. So what this question is asking you is, it is asking you for the time interval over which your object is more than 8,000 feet. So let's say right about here ends up being that 8,000 feet mark. We want to know how long is that projectile going to be at that height. So obviously everything above 8,000 would be considered as part of that interval. So we want to know how long is it going to take. So when is it going to hit 8,000, and then when is it going to come back to 8,000 and go down. So that means my h of t is 8,000 feet. So we have to then use that in our formula. So I have 8,000 feet is equal to negative 16 t squared plus 1100 t plus 200. Okay. So the first thing I need to do is I need to move this 800 over, because in order to solve my quadratic, if you remember, you always need to have it set equal to 0. So this becomes negative 16 t squared plus 1100 t minus 7800. From here we have everything we need. To solve, you want to make sure that you use your quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. So to solve that using the quadratic formula, says the first thing you need to do is you need to identify your a, which is negative 16, your b, which is 1100, and your c, which is negative 7800. You then have to plug into your formula. So here we're going to have negative 1100 plus or minus the square root of a whole bunch of stuff. So we've got 1100 squared minus 4 times negative 16 times negative 7800, and the whole thing is over 2 times negative 16. So you want to simplify that. The easiest place to start is to simplify with inside your parentheses here. So when we do that, we may end up getting a large number, so you're going to go ahead and take your calculator and you're going to do open a parenthesis, and you can do 1100, square it, close your parenthesis, and then I would subtract and open a new parenthesis and do 4 times negative 16 times negative 7800. And then you're going to take the square root of that value. So here the value that you should get is going to be 710,800. You're then going to take the square root of that value, and that's going to give you a decimal. And at this point, that's okay to get a decimal. And the reason it's okay is because we're dealing with time, and time is given in decimals. Notice it says round to the nearest hundredth. Okay. So we then have to do my negative 1100 plus or minus. The result that we get is 843.0895563. And if I were you, I would make sure and use as much of the decimal as you can, because remember, the earlier you round, the more it changes your problem. So when we reduce this, we're going to have to do negative 1100 plus my 843, divide that by 32, and then we're going to have to do negative 1100 minus my 843, divide that, and here you should get an interval that goes 8.03 to 60.72 seconds. Okay. So if we're talking about what does that actually mean, it means our projectile will be more than 8,000 feet from 8.03 seconds to 60.72 seconds. Okay, so that is what we are doing, and that's what answers your question. Okay. Now the second example I have is a little bit more, has a little more to it. So first of all, it says that Whispertown has a population growth model of P of t, or PT, equals AT squared plus BT plus P naught. Okay, so this is the foundation that we are starting with. And it says where P naught is the initial population. The problem goes on to say, suppose the future population T years after January 1st, 2012. So we know January 1st, 2012 is an important piece of information. And it says is described by the model right here. So here in this problem, it's actually filled in the quadratic equation for us. So we just simply have to solve the problem. So the first part says, what is the population on January 1st, 2020? So when we are looking at the time, we are going to go from January 1st, 2012 to January 1st, 2020. Means the only thing changing is the years. Therefore, you can take 2020 minus 2012 and you get that this is an 8-year difference. Okay? Therefore, this is my t value. So anywhere I have a t in here, I have to substitute 8. So this becomes P of 8 is equal to 0.8 times 8 squared plus 6 times 8 plus 24,000. So we're going to go ahead and you would do the math. So 8 squared is 64, multiply that by 0.8. Then you're going to add that to 6 times 8, and then add that to 24,000, and you should come out with 24,099.2. However, we can't have part of a person. So when we're talking about the future population, we would round down to saying that we would have 24,099. The future population is 24,099 people. Okay. Now, the second part says what month and year will we reach 30,000. So this is telling us that we have our population equation being 0.8 t squared plus 6t plus 24,000, and we want to know how long it takes for this to equal 30,000. So we need to again solve our quadratic. So we got to set this equal to 0 by subtracting that 30,000. So we get 0.8 t squared plus 6t minus 6,000 equals 0. And again, you want to use the quadratic formula. Which is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So this being said, you want to plug in. So we know that a is equal to 0.8, b is equal to 6, and c is equal to negative 6,000. So we got to plug our information in. So you're going to have -6 plus or minus the square root of 6 squared minus 4 times 0.8 times -6,000. And that whole thing is over 2 times 0.8. And when you solve this, you're going to come out with two answers. So this is your t. So we're going to come out with the answers 82.9 and -90.4. Well, of these two answers, we can only use one of them. And in this situation, we can only use my positive. And the reason for that is because we can't go backwards in time. So here, the 82, again, we are looking at the whole number being years and the decimal being months. So here, to find years, we need to add the whole number to our starting year. So in other words, we started in 2012. We are going to add 82 more years, and that is going to give us the year 2094. Now we have to find months. So to find the months, we need to multiply the decimal by 12 months. So here we have 0.9 times my 12 months is going to give me 10.8. So when we look at this, the whole number is going to tell you the number of months. Okay, so here the whole number gives the number of months. So here we have 10. So what this is actually telling you is that we are most of the way through the 10th month, okay, or that we are through the 10th month, and the 0.8 tells us we are most of the way through the 11th, okay? So the whole number gives the number of months completed, and the decimal gives the partial month. Completed. Okay, so what does this actually mean? Well, what this actually means is that if you think about your months, okay, the 10th month or October has been completed. The 11th month, which is November, has been partially completed. Okay. So therefore, to answer the question, the month and year of reaching 30,000 would be November of 2094. Okay. So those are some of the more complicated quadratic applications that occur when we are solving and working with quadratic applications and problems. So if you have any questions, please let me know. Otherwise, see you next time.